Hello there. So let's continue with this case, transition to turbulence, the 3-element airfoil. So now let's see the case setup. So here I already load the case. Okay, so remember you don't load the cases, so you should have the Fluent directory, and here you should have the files. Here in the output you have another solution with the coefficients you want to compare. I'm not going to run, as I mentioned, because this is a little bit long case. You need to run like 2,000 iterations. Okay, but just to go through the steps. Okay, the first things that I want to show you here, so look at that. Okay, the meshes are super fine, but interesting that we're going to do some sampling somewhere there, and we have a line there that I already put here for you. Okay, so just let me just deselect here. So we're going to sample velocity in that line, and the question always arises that, okay, how do you know, how do you plot that line? Remember, they have to be normal to the wall there, but you have the airfoil coordinates. So you have also in your files, you have the space clean. We already went through this, how to import the airfoil coordinate, but basically you can go in a space clean and find where to put it. Now, so you're going to draw the line that is normal. You have all the constraints, everything here. So that is how you do it. Also, if for any reason you get the mesh and you don't have the geometry, remember that you can extract the coordinate from the mesh. So you can go here, like here, now the XY plot, and then you just select the geometry and then mesh, select coordinate XY or whatever, and then you have here and write that file. Okay, so this is how I did it, by the way. So I had the mesh, but I didn't have the proper coordinate. I started from here, and that's all. Okay, so let's go in the case setup. So let me go back here. So again, we are, as usual, I will use the vertical workflow. So we go here, general, nothing to do, a steady. I'm going to stick to the pressure base. Then in models, here's where we enable the models. Okay, so as usual, I'm using the transition SST, but you can use any of the models that transitional models, and also standard Turbulence models, and you can compare solutions and see that you don't get same results. Okay, you have these corrections here. Later in the next videos we're going to address these corrections, but also we'll address this in the theory. Okay, so I'm not going to talk about that. So for the moment I will choose this one. Okay, the case is set up. We have the material. And I would like to stop here in boundary conditions, because there is a particular boundary condition here. So as you look at your domain, look at there is a very large domain and you have it here, but everything there is called far field. Okay, so there is a particular boundary condition that you can use it there. This boundary condition is only available when you are working with compressible case. So see that the energy equation is enabled. Even the Mach number is like 0.2. Okay, I enable that to get access to this boundary condition. And the advantage of this boundary condition is that here you just need to set the Mach number and the incidence angle. That's all. Okay, so the boundary condition automatically will do the treatment to see when the flow is centering and going back. Instead, as you recall doing with compressible flow, in compressible flows, the standard one, velocity inlet, pressure outlet, you need to set up all that manually. Okay, so this is an advantage that you have with that boundary condition. So as you go here, you will see that you select here that would be far field, and see that you have it there. It's called pressure far field. So see our Mach number, our incidence angle, and see that as usual we have our initial conditions entering there. So see the intermittency always 1, and then low turbulence intensity. So you can play with this one. You will see the influence in the outcome. So that's all that I wanted to mention. Then the rest of the boundary conditions are standard. Here we have the reference value, how we normalize to compute coefficients. Remember, this is only used to normalize. Also for turbulence intensity, okay, that value is computed using this velocity. Okay, so if you're curious to know how it's computed, the turbulence intensity is using this value, so you should set it also according to your to your working conditions. So in methods, let's stick with the traditional method decouple. Again, you can try many other methods, but in this case, this one will give faster. Well, actually, in this one, it won't give faster convergence. Maybe if you use a simple, the computational cost will be lower. It's up to you to try. So this option, leave it as they are. Okay. And here we set all the monitors. So see that we have all these monitors, Y plus max, maximum Mach number, velocity average. I think this is in a given point, so I put there a point to monitor. So that point is a point somewhere here. So let me go, let me see, where is that point? So see that point here. So monitoring velocity there. So you start to put all your monitors. This is very important. Standard monitors will be lift drag coefficient and y plus. Average and maximum here, I only have the maximum, which should be both of them, average and maximum. Okay, and then plot, save to a file, is up to you. You have your residuals, initialize your solution, and you are ready to go. So in this case, okay, I'm not going to run, I just showing here, okay, let me initialize just to run a few iterations, and then I will reopen the file, the final solution. So if you press extract, okay, yes, calculate. So you're going to launch all your monitors, CD, everything standard, nothing changed. Okay, the usual case setup. Okay, so again, remember I mentioned that intermittency, sometimes it's difficult to make it converge, so don't be surprised, okay, if it stay stalled or relative large values. So I will stop here. Okay, I don't want to run because it takes long this case. Okay, so here you have that. Do not override that because you already have a solution there. Okay, so in output, let me copy also these values here, CD, to show you the history of CD and CL. So after you run this case and you get your solution, so let me show you the residuals. So I will plot. So see that I disabled the convergence. Okay, remember this needs to converge well. So see that it run probably after 800 iterations, the residuals got stalled. This is not an indication. This is not an anomaly. This is normal behavior. There are ways to overcome that. I'm not going to address that, but don't be worried about this. Okay, but see that it takes a long time. Okay, so it's residuals going down and then stabilize there. I see that almost 2000 iterations, 1600 iterations I run this case. And then also we have here the CD and CL. So let me plot this, okay, and see that. Let me change also the axis. Okay, so let me change this one. It will be from 0 to 0.25 maybe. Okay, so see that we have this behavior, and see that in correspondence to this residual, see that they're going down, and then about 800, see that now about 800 seems get a little stable. But see that there are some oscillations, they are small, but these oscillations, usually you see this one, it is a good indication, or that is the fingerprint of some unsteadiness. Okay, so unsteady behavior that we will expect here, because remember, we're 20 degrees. Okay, so we should have that shed in there. Okay, so and the same, you can plot the same with CL. Okay, so let me plot CL. See, we have it here, and see that we have the behavior here. The residuals got stable in about 1000. So see that they are not necessarily at the same value that the one get stable, the other will get stable. So see that there is kind of a phase difference there. Okay. So that's why you need to monitor many things at the same time. Okay, I didn't save for the other values. Okay, so I don't have that information available. So this is how you run this case. Okay, pretty much it will run very smooth, and now we can do our traditional post processing. So see here that we have velocity magnitude, and now as it is incompressible, I can go and use Mach number. See that we have the Mach number there. And what is interesting that we have, even it is incompressible, see that it's quite funny that we have supersonic now. We are reaching the critical Mach number. Okay, so we have some high speed regions there. Okay, so see that is now as you run incompressible, you will see that there are some differences in velocity, but see that we have this high speed region there. Okay, we can check also pressure. And you have your traditional there pressure plot. Okay, and so on. Interesting, as I mentioned, a good indication to see if you have a good mesh to resolve the boundary layer would be the eddy viscosity ratio. Okay, so that is a quantity that people that do not spend very often, and it turns to be that it's very important. Okay, it tells you a lot. So see that this is what we have, and if I zoom in, okay, see that kind of you start to see here that these are the regions where you have more turbulence, okay, kind of also will indicate your boundary layer and see there. So let me change these scales and put here probably 500. Okay, here we see better. So see here that you can see the transition. So see that everything that is 0 means that you don't have turbulent viscosity. See that boundary, and then here see that, start to see that turbulent viscosity. Probably if I reduce a little bit more, you can see better. See that kind of here will be your point of transition. Okay, and then as you plot your mesh over this one, you will see that you have a good mesh to resolve the boundary layer. Let's see if that is the case. Okay, so see, this is what I would mention. Okay, so what has been mentioned. So this is, in fact, this is a very good mesh, okay, to resolve the boundary layer. And remember that usually the turbulent viscosity ratio peaks in the middle of the boundary layer, so you should check also always that you have a nice transition like in this case. Okay, so there are many quantities, many things that you can plot. So static pressure there. So, and let's take a look at the intermittency. It is that marker or that switch that is telling you whether you have laminar or turbulence. So as we already evidenced using the turbulent viscosity rate, you see that here you have the laminar region, here you have the onset of the transition, and then see that very, very narrow region, the viscous layer, you have it there. Then we look at the airfoil here, and very similar. So let's plot here. See that now you have that the turbulence model is starting to work somewhere here. Okay, so we can put, let me put in an indication there to see the correspondence. So if I put here a line here, so kind of here, okay, and let's change here. So yeah. Okay, so now enable intermittency and see that it corresponds. So you have here laminar, and then you transition, and then here is where your flow becomes turbulent. Okay, so this is the traditional now case setup. Okay, so I invite you to play around. So remember that we're running a large angle of attack somewhere here, but you can rerun this one like 0, 5, 10, 15, 20 and try to reproduce these results. There you will have the files. Let me check, I think. Okay, you have the experimental data, but you can use that plot, and also in the reference you have the values. Okay, so what else we can do? We can plot also over the surface. So we have the elements there. We can do the plot of pressure coefficient. We have CP. Okay, so we have those plots here. Okay, there are many things that you can do. So let me do CP distribution. Okay, so you select your elements. Okay, so see that flat bottom, top bottom. So you select, so here we're plotting all the elements. Okay, and it's divided in top and bottom, intra-dose, extra-dose. And let's open also the validation data. This one, have CP experimental, and see that we have a relative good agreement. Put it there. Okay, probably you will need to zoom in and you will see some differences here, but this is very acceptable. At a larger scale, it's a good agreement. All the things that we can plot. Okay, so remember here we have transition to turbulence, so we check some colors, but also we can quantify skin friction coefficient that we have it there. So let me plot it, this one here, and see that this is skin friction airfoil top. Okay, just in the top part of the airfoil will be this one. So we're just plotting here in the top part. Okay, and see that if you look at this, immediately you will recognize this behavior similar to the flat plate. You have here, it's correlating to a laminar solution, and now here you have the transition to turbulence and become completely turbulent. If you run this case now using a spiral maras or traditional SST model or KETS, you will see that those models will fit to this curve here. So actually I think I have that one to show you. Okay, so if I go here, I already now put a solution there, and I think see that you have CF for spiral maras airfoil top. And see that I put it there, and this is what this parallel model is giving you. Actually something midway between laminar and turbulent. Okay, so see that you have all these differences that you will need to quantify. This, at the end of the day, when you integrate your whole CL/CD, you will see that it will have an influence of probably 10, 25, 2%, who knows, you need to quantify, but it will have an impact on your solution. Okay, so the final part that I want to show you here is the plot of the Y plus. Okay, so I show you that here, I'm plotting here, I chose this point is a random point because I like it, but you can put it whatever you want. So interesting that probably you can do the same plotting here where the flow is laminar, and you should get the solution that we know, but you should get the fit into the viscous law, not to the log law that we're going to get here, that we know here is fully turbulent. Okay, so to do that one, remember, line normal to the flow, sample wall shear and stress, also sampling density and viscosity. So in the previous case, they are incompressible, so you know the value. But here I set up the monitors, and actually I'm setting all these monitors like this. So in this line here, we have moon, raw, wall shear stress, and using that information, you will set here your derived quantity, your custom field, so you get the shear velocity, and then compute Y plus, U plus. Okay, so you compute the Y plus in this line, normal to the wall. So let me go up here, manage, and see. Shear velocity, you are using this information, this monitor that you have here, divided by the square root. Then Y plus, okay, you have density, you have the shear velocity, and the boundary normal distance. Okay, this is the distance normal to the wall. Okay, actually I think it's better to use the cell wall distance instead of this one. Okay, there are two. Okay, and then we have U plus computed like this. Okay, so in literature you will find that it's recommended to use the component, okay, to decompose this one normal to the wall, but I think the differences are small, so using velocity magnitude is okay. So that now that you have this, you can do your plot. So we have it here. So let me go here, and this is our plot. Save, and see that we have that. And then we can compare that. Usually we have some results. And remember that you normalize this one. Doesn't matter the geometry, what you're doing, you should always get similar results. So let me load everything. And voila. Okay, so see that we have this result for NASA. This is for another geometry, another case, another condition. So I don't care, but as soon as I normalize that one, I can reproduce or recast the same profile. And then we have the traditional, the viscous layer law, and then the log law and the Spalding law. And see that our profiles match very well. Resolving here, blending, log law here, wake here, region. And then you have this is funny behavior, but this is mainly due to the separation, to the secondary jet that is influenced by the velocity there. Just to remind you, what was that? It's this secondary jet that you have here. So remember that you have the flow like this. Okay, so it's a flow coming, entering at a large angle of attack. Here you see the influence, and probably you can also put vectors just to see things better. Let me skip here 2. And sometimes you have to be careful when you put this vector, because you have very fine meshes. It will take some time to plot everything. Okay, so likely maybe it crashed. Okay, yeah, I think. Okay, I forgot to select the flow. Okay, so it's not plotting anything. Why? No, Okay, I don't. Okay, I need to scale. Okay, let me go back. Vectors. Probably increase the scale to 0.2. Okay, so you have it here. So see that it's a large angle, and you have the behavior here. Kind of very nice recirculation here as expected. Okay. Then here, see that you have also, I think somewhere you will see that the boundary layer is detaching here towards the trailing edge. Okay, so then you analyze the flow, and you just need to give, you know, that give it that physical interpretation. See here that you have the separation. So in reality, for this angle of attack, yeah, here there will be massive separation. Remember here the averaging and everything. Okay. We are smoothing, let's say, let me use that term, we are smoothing the physics. Okay, so that's all for this case. Okay, so at this point, just feel free to run, and just the warning that it may take some time. Now because you need to run it, this one in particular, you need to run it for like 1500, 1600 iterations, but also try to use different methods, okay? Because the couple here, from a computational point of view, is quite heavy. So probably using simple or simple C, it will give you a faster outcome, okay? So it's up to you to test that. Okay, that's all for this case. Thank you very much for your attention. See you next time. Bye.